Doing Every Challenge Question Part 38, I believe, is the review chapter 1 from Core Pure 1. I quite like it when they do this. This is just a question that is in FP2, like it's just a topic in FP2. It's about drawing loci look like this. Edewu has a brilliant series that you should be able to find if you YouTube Edewu major and minor arcs, complex numbers, something like that. That'll get you there. But yeah, this is just from FP2, which makes it very easy for me because I have watched Edewu's videos and I know how to do FP2. So this question is not much of a challenge. Obviously, you get your imaginary and real axis out. The Z minus 8 means you're looking at the point 8 and the point 2 here. And of course, the argument of Z minus 8, if I just call the argument of Z minus 8 alpha and the argument of Z minus 2 beta, then therefore the argument of Z minus 8 over Z minus 2 is alpha minus beta. That's just how arguments work, right? So if we just draw a line coming out of this point here, this is going to be alpha, because that's what I've defined it to be, and this is going to be beta here. Of course, this is a straight line, so therefore this is pi minus alpha. And then if we consider this angle here, this is pi, because that's how many radians are in a triangle, pi minus alpha minus beta, which actually just has to be alpha minus beta, which is the argument that this here is talking about, right? So this is the key angle here, and apparently that needs to equal pi over 2. Now, this is where we need to go back to GCSE for a second. You might remember this circle theorem that says that the angle in a semicircle is pi over 2, just here. What this actually means, and when we think about circle theorems, we usually start with the circle and then draw some lines in it, and you come up with an angle theorem. That's not really how circle theorems have to work. You can do them the opposite way around. You can come up with two random points, and you can say, okay, if I want to point a laser beam out of each point, and if I want those beams to meet at 90 degrees or pi over 2 or be perpendicular, then what that means is the trace of points that where this could be, such that I always make perpendicular lines here, traces a semicircle around, right? You can arrive at the circle at the end rather than starting with it. These are if and only if conditions. They work both ways around. So okay, another way to draw it would be over here somewhere, and you end up with a 90 degrees over here, which is cool. And so that means all the points that I'm searching for that create this to be pi over 2 are just a semicircle going around from 8 to 2. So that's the loci, just there. Deduce the value of Z minus 5. Now remember, this was 8, this was 2, so 5 is bang in the middle, which means this is a semicircle centered at 5. And of course, the distance from 5 to 8 is 3, so the distance from Z, which is somewhere on this arc here, to 5 is always just 3. And that'll be the question done. Do have a look at the FP2 book if you have access to it, and watch Edewu's videos on that because they're great. Okay, back to series then. So this is very similar to something that we did in the series challenge questions video here, where we have to come up with a function that makes this here. Now I know the function that makes a quadratic, it's just this simple r here. Of course, if I double it, I make this. And now this is very close to this, right? So ur is almost just 2r. It just has not the right number of n's in the end. But I can make more n's by just doing this. The sum from 1 to n of 1 is just n. So therefore, if I times everything by 4, I'll get 4n. And if I could just combine these two results here, I'll get n squared plus n plus 4n, which is n squared plus 5n. And this will be the function that I need to use at 2r plus 4. So that's that. Show that this thing is this. So okay, I have that this is 2r plus 4. The sum from n to 2n is obviously just the sum from 1 to n. Take away the sum from 1 to n minus 1, because I just need to remove all the terms up to n if I'm going to start at 1 here. And of course, I can just do this. You can split it into 4 things, or actually you can just use, of course, I'm being an idiot, just use the result that's above, right? Just say, I know that this here is n squared plus 5n, where n is the top number. This time it's 2n. That's 2n squared plus 5 lots of 2n. And this thing here is n minus 1 squared plus 5 lots of n minus 1. And I'm taking away, of course, just to expand everything out. And then you can factorize at the end, and you end up with what they wanted you to get, which is great. So that's that done. Number 3, again, very similar to something we did in the roots chapter here. W is x squared plus 1. Take away 1 square root. The plus or minus isn't going to matter, and you're going to see why. Just put that result into here. Now, this obviously here is just w minus 1. And now this here is w minus root w minus 1 times root w minus 1 times root w minus 1. But of course, the first two of those things just make w minus 1. So it's going to be this. And now what I'm going to do is I'm going to say, well, here's w minus 1 lots of this, and here's 11 lots of this. I can collect those two things together to make w plus 10 lots of that thing there. I can of course also expand out and collect these things together. I'll move everything onto this side of the equation that's not root w plus 1, or minus 1, sorry. And now I'm just going to square both sides, and this is why the plus or minus didn't matter. It would have gone away anyway. So I'm going to square both sides here. Square this carefully out, so it's 5w plus 10 times 5w plus 10. This is w plus 10 times w plus 10. It ends up being this. Multiply that over there. Again, do a bunch of expanding. You end up with this. Collect everything on one side, and you end up with this here, which I believe is what they wanted to get. Thanks for watching, and I'll see you next time.